All right, let's start this story at the beginning. Welcome back. So let's talk about the birth of the universe. Probably a good place to start. Oops, let me get going here. Okay, so the origin of the universe, it developed initially from the Big Bang. More on that in a second. That occurred approximately 13.7 billion years ago, give or take a point billion or so. The Big Bang Theory is the model for the evolution of the universe. So Darwin's theory of evolution is biotic evolution. The Big Bang Theory is the evolution of the universe. Things change. That's just how the whole universe works. So here we are. So the Big Bang Theory, again, highest level of knowing, testable, repeatable, never been proven false, widely accepted. This isn't a guess. This isn't an opinion. This is science. So let's talk a little bit about the Big Bang Theory and how we got there. So we know that the universe is expanding. I mean scientists. We know that the universe is expanding. The reason we know that, we can see it. We can see galaxies and things moving away in all directions. Now, there's a little bit of physics behind all of this, and I'll get into that again. Not that I'm assuming you need to know any physics or you've ever taken any physics. None of that. I'll try to explain it best I can. So the way the universe is expanding, it's kind of like a loaf of bread. Right? Imagine you're making raisin bread. So you got the dough with raisins in it. So it's a compact, dough, and you put it in the pan. Well, as you bake, that bread kind of expands. And when that happens, all the little raisins that are in that raisin bread kind of move with that bread as it expands. So imagine the bread being the universe and the raisins being, for example, galaxies. And so the further away things are kind of initially or in the beginning, the even more further away it's going to be as time goes on. So things are going to be moving at different speeds relative to where you are. All right, so let's say this is our home raisin, right? The closest, the next raisin to us is 3 centimeters away. The furthest one is 20 centimeters away. So let's say after an hour of baking, here's our home raisin. That next closest raisin is now 6 centimeters away. So it's traveled 3 centimeters per hour, a distance in some amount of time, at speed, 10 miles per hour. So this raisin has traveled an additional 3 centimeters in 1 hour. Well, the furthest raisin from us went from 20 centimeters away, now 40 centimeters away, in that same amount of time. So it's traveled 20 centimeters away from us in 1 hour. So it's traveling 20 centimeters per hour. That's 6+ times faster than the raisin closest to us. And that's what happens when things are kind of expanding. The closer things are initially, the kind of slower it appears it's moving away. The things kind of initially that are further away appear to be moving a little bit faster, even though this whole bread is expanding kind of at the same rate. Same thing with the universe. Let me just go back a slide. Even though the universe is kind of all expanding at the same rate, stuff that's already further away appears to be moving faster, stuff that's closer, not so fast. That becomes important. All right? Another aspect of this whole thing, and I'll try to kind of get it all together, is something that we experience from time to time. All right, so 1, evidence of the Big Bang, universe is expanding in all directions. All right, that's number 1. Again, galaxies are moving away from each other. When they do, and the speed at which they do, they create something called a redshift. So more on that here in just a second. It's a physics-y astronomy thing. But it's rooted in the same idea as if you were standing and heard a train horn. And this is all related to something called the Doppler effect. Imagine you're standing and something's coming towards you, a train, an ambulance, a police car, or a car honking their horn. As it's coming towards you, you hear this horn or siren at a little bit higher pitch, and then once it gets past you, the pitch, the frequency drops a little bit. So, let's say an ambulance is coming to you, wee woo, wee woo, wee woo. As soon as it passes you, wee woo, wee woo, wee woo. It's a pretty good impression. The pitch drops a little bit. Or with a train horn, it might be coming at you. car horn. That's the Doppler effect. And it's not that the horn is changing its sound. It's still making the same sound. But how we hear it is different based on the movement and the speed of this thing relative to us. Remember back to about the raisins, how the further ones are moving faster, the closer ones are not moving as fast. So this Doppler effect has to deal with things moving, the speed of which things moving, and how waves of sound in this case, or when we're talking about the universe, light, kind of change a little bit. And that's all due to this Doppler effect. So again, same with a car. It's still making the same noise, but as it's moving towards you, all those sound waves are kind of packed up. The frequency at which those sound waves hit your ear, they hit it real quick. That is a higher frequency, meaning those sound waves are hitting your ear faster, which is going to create a higher pitch. When it passes you, still the same sound waves, but they're not going to hit your eardrum as frequent as it moves away. So the frequency is lower. A lower frequency sound is a lower pitch. High frequency, low frequency. Same thing with light. And this is how we're figuring out that the universe is expanding. Okay, same thing with light. So quick background. As different elements give off light energy and absorb light energy, it gives us different spectrums. So what we're seeing here are absorption and emission spectrums for different elements on the periodic table, little chemistry. So hydrogen, when we send pure white light, which is composed of every color of the rainbow, through gaseous hydrogen, when we look at that light on the other side, it's missing kind of some of these bands. These are called absorption spectrums. So each element kind of has a different absorption spectrum. So the way we can tell a distant star is made of a certain gas, or even our own star is made of a certain gas, or the way we can figure out the atmosphere of the consistency of Jupiter's atmosphere is by looking at these. We know hydrogen has these kind of black absorption spectrum lines. Helium lines look like this, carbon, nitrogen, and oxygen. So we can assess what the atmosphere of Jupiter is made of. We can assess what the sun is made of. We can assess what distant stars and galaxies are made of based on these and based on where these lines are. Okay. For instance, let's say I'm looking at a distant star and I want to know what it's made up of. For instance, our sun is mostly hydrogen and helium. And I'm looking at the light from the star and it has these absorption spectrum lines. So which gases match up here? Well, let's see. It looks like, so this line here, this line here, this line here. So in this particular star, it looks like there's some hydrogen. What else might there be? Oh, it looks like this kind of matches up. These two lines match up. Oh, and helium. It looks like whatever this star is kind of the majority of what it's made of, it looks like it's mostly hydrogen and helium. Okay. So we can do the same thing with other stars, atmospheres of different planets, distant galaxies. However, these patterns of lines will still be the same, but as due to the Doppler effect, not only with sound, but with light waves as well, as something is moving away, it's what's called red shifted. It's shifted more to the red spectrum. So looking at this example, all right, so say this is kind of normal absorption lines of some particular element. Well, if I see those same pattern of lines, but they're kind of shifted more down towards the red region, that's called a red shift. That actually lets me know that something is moving away. This light source, this galaxy is moving away. If the lines are shifted more towards the blue, that's called a blue shift. And that actually means this light source is actually coming closer. It's like the Doppler effect, but with light, not with sound. Again, at rest, there's, some particular molecule or element has this absorption line spectrum. Again, if it's moving away from you, all of those are shifted more towards the red. If it's moving towards you, all of that is shifting towards the blue. Not that it will all of a sudden appear blue or red, it's just these lines are just shifted one way or the other. We don't really see too much of a difference visually, but we can see it where these lines are located. So kind of, yeah, as an example, something moving away, red shifted, something moving, a galaxy moving closer, all of these lines are blue shifted. Not that visually they become red or blue, it's just where those lines are on the color spectrum will change a little bit. All right, so the universe is expanding. That's evidence number one. And there's also this random weird background radiation at about 2.7 degrees Kelvin, which is actually really, 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 really cold. So everywhere we look, not visually, but we can have telescopes don't only see visible light, we also have telescopes that will see in different spectra. And one of those is microwave background radiation. And so everywhere a particular telescope looks, if it's sensitive enough to see microwaves, which is on the spectrum of light, we can't see it, but with special telescopes, they can. We can't see it with our eyeballs, but special telescopes can. Everywhere we look, we see this cosmic background radiation, CMB. This is leftover radiation from the Big Bang. When that initial Big Bang, that expansion happened, this kind of heat and background radiation kind of is just everywhere as the universe is expanding out. And this is kind of a visual image of what that looks like. So we had the Big Bang, we had the initial inflation and that afterglow, that radiation back in time, and we see the universe expanding, and we have the evidence for all of that. Again, testable, repeatable, never been proven false. So how do we determine the age of the universe? Well, we just measure how things are moving away, and we run that kind of backwards. All right, if I see the speed of all of these things moving away, if I can measure how fast these raisins moved away, well, let me just run that model in reverse, and we can come up with a timeline of when all of those things must have been together. So again, yeah, just instead of things expanding, just kind of run that in reverse. And how much time would that take? And that's how we got to 13.7-ish billion years into the future. So when the universe began, all matter and energy was compressed, kind of in this infinitely small, high temperature, high density state. Time and space was set to 0. Gets a little complicated, just take my word for it. During the first second after the Big Bang, the 4 basic forces separated: gravity, the electromagnetic force, strong nuclear force, and weak nuclear force. More on that in physics and chemistry if you ever need to take it. Then an enormous expansion occurred. About 30 minutes after the Big Bang, nuclear reactions had kind of completely ended and things kind of began to be as they were. The universe's mass consisted almost solely of hydrogen and helium nuclei, just the nucleus, not necessarily the electron parts, so just the nuclei. The continued expansion and cooling began to coalesce these molecules and atoms and produce stars and galaxies. And the composition of the universe began to change, because initially it was just hydrogen and helium, and the heavier elements, now that we have, if you look at the periodic table, formed during the kind of death of stars. I mean, it's a lot to digest, but just know that the story begins with the Big Bang. We have evidence for it. With the expansion, we see things moving away, and the cosmic background radiation, we have that afterglow. Like when you see an explosion in a movie, how that kind of radiates outwards. So kind of the same thing in space. That leftover bit, of the Big Bang, of that expansion, we see no matter where we kind of point these particular telescopes that can see microwave radiation. So it's all testable, it's all repeatable. We see it. You run that kind of model in reverse, and it kind of would take about 13.7 billion years to come back together. All right. So we talked about the birth of the universe. When we come back for section 5, we'll talk about the birth of the solar system. We're going to take this story kind of in order. I'll see you back here in just a second.